Okay, so welcome back. Let us take one example of a line which supports TEM. There are many examples. One of them is coaxial cable. One coaxial cable, it can support TEM as well as TE and TM wave. But since TEM, it does not have any cutoff frequency, it will appear first. And if we keep on increasing the operating frequency, so first transverse electromagnetic mode will appear and then transverse magnetic mode will appear. So we are talking about monomode bandwidth operation. We will see the electric and magnetic field orientation is different for these three different lines, and in practical design we can only deal with one single mode. So that is why it is always preferred that for a given transmission line or guiding structure we will be using the fundamental mode. So for coaxial cable it is TEM wave, TEM mode. So let us take one example here. So it shows the coaxial cable, it comes in different forms. It is very popular at microwave frequencies. At millimeter wave frequencies it becomes lossy, but since it has the advantage that we can easily turn it and also twist it, it is usually used with the measuring instrument. So this transverse electromagnetic wave, any guiding structure that is supporting, it can be represented by a transmission line. It is a two-wire line. So for this one, then we can easily calculate what is the input impedance of the line, what is beta and what is alpha of this transmission line. Let us consider this scenario. A coaxial cable, it is connected to one millimeter wave source which is represented by the voltage source and its internal impedance ZS, and it is terminated by a load, complex load, it is given by ZL. So in that case the input impedance Zin as seen by the source, that is equal to Z0 into ZL plus JZ0 tan beta L. So this beta L, this is nothing but electrical length of this line theta divided by, we have again Z0 plus JZL tan beta L. So the input impedance, it is a function of ZL and Z0 as well as it is a function of beta L theta. So if we keep everything fixed and then we change the frequency, operating frequency, then the input impedance will change, since it is a function of beta. Beta is equal to twice by lambda g. So sometimes you will see that we use distributed forms like this one, using resistor, inductor, conductance and capacitor, and we represent a transmission line. But what is the difference between the left figure and right figure is that this right figure, it can't predict periodicity of a transmission line. Anyway, so whenever we have a transmission line like this, then for this one we have some closed form expression. For example, the guided wavelength lambda g, this is approximately lambda naught by root epsilon r. Electrical length already we have seen, theta is equal to beta into L, and propagation constant beta equal to twice pi by lambda g, phase velocity omega by beta, and group velocity del del beta of omega. So next is TE wave. One popular guiding structure that supports TE wave is rectangular waveguide. So in this case, by definition, Ez equal to 0, since we are considering propagation in z direction, and Hz that not equal to 0, and beta, this is equal to root of k square minus kc square. So we have a cutoff wave number here that can be given by square root of k square minus beta square, and which is not equal to 0. So it can't support DC, it has a cutoff frequency and it will support electromagnetic wave propagation only above that cutoff frequency. In this case, we can't calculate voltage or current directly, and we can't define the characteristics impedance of the line Z naught, but we use another term which is called the wave impedance ZTE. For TE wave, it is again Ex by Hy, and it comes omega mu by beta or k eta by beta. Usually a closed conductor, and not only that, two or more conductor system also can support TE wave. Next is TM wave. It also have similar property like TE, but in this case Hz equal to 0 and Ez is not equal to 0, and the cutoff wave number Kc, this is equal to square root of k square minus beta square. So, just like TE wave, in this case also we have a cutoff frequency, and wave propagation starts above cutoff frequency, and the wave impedance is defined as ZTM equal to Ex by Hy, that is equal to beta by omega epsilon or beta into eta by k. So, again closed conductor, two or more conductor system can support TM mode, and we can't define characteristics impedance for TM wave as well. So, next let us see what is surface wave and what are the problems we face due to surface wave. So, let us start with the dielectric slab. We are considering wave propagation in z direction, and this dielectric slab, it's infinite in xz direction. So, y is the perpendicular direction. We are considering origin at the center of this dielectric medium. It can be shown it can support TM and TE modes, but not TEM mode, since we do not have at least two conductors. So, TM mode, sometimes also known as the E modes. In this case, the electric field is parallel to plane of incidence. So, if I consider this diagram, so electric field it's incident at the dielectric air boundary, and the plane of incidence is YZ, and then according to definition for the electric field, we have only Ey and Ez component, since E is parallel to this plane, and since it is a TM mode, transverse magnetic. So, in Z direction we do not have any H component. So, then the dominant electric field component, electric and magnetic field components are Hx, Ey and Ez. Similarly, for transverse electric case, sometimes we also call it M modes. In this case, H is parallel to plane of incidence or Yz. So, Hz is not equal to 0, and we have Hy and Hz component and as well as the Ex component. So, the relationship between the propagation constant and attenuation constant can be given as beta square equal to k square k naught square plus alpha square in z direction, and field decays from the surface as e to the power minus alpha y minus t by 2. So, mostly the electric or magnetic field components, it will be inside the dielectric. If we go above this dielectric inside air, or if we consider below this dielectric, electric field or magnetic field components, they decays exponentially. Let us start. So, let us first consider the TM mode. So, for TM mode, as we have seen from this, electric field is parallel to plane of incidence. For TM mode, again we may have two different scenario. In one case, z equal to 0 at y equal to 0, and with this the variation of Hx with respect to y, that is also equal to 0. We call it symmetric mode, and if we solve for the field components, so let us consider the magnetic field, since we have only one magnetic field components in this case sorry, Hx. This is equal to a sec of Pd cos Py. This is inside the dielectric, and outside the dielectric it varies exponentially, as we observed in previously. And for the antisymmetric mode, Hx component is 0 at y equal to 0. So, y equal to 0 means this dotted plane or the zx plane. So, on this plane for antisymmetric mode Hx equal to 0, and not only that, variation of uy with respect to z, that is also equal to 0, and in that case Hx above and below the dielectric it decreases exponentially, and inside dielectric we have a sinusoidal variation with y. Let us consider the first two modes. The first symmetric mode, that is called TM0 mode. It does not have any cutoff frequency. This is very interesting. So, we are plotting variation of Hx with respect to y. So, we see that inside the dielectric slab on the mid plane, that is zx plane, Hx has maximum component, and in air it decays exponentially. And right side, this is the first antisymmetric mode, we call it TM1 mode. So, as expected, on zx plane Hx equal to 0, and inside air again it decays exponentially. So, for the TE modes we can also solve similarly, and we also have symmetric modes and antisymmetric mode. For symmetric mode, Hz equal to 0 at y equal to 0 on this plane, and for antisymmetric mode Ex equal to 0 at this plane, and we have similar variation of electric field component Ex like the Hx variation of TM mode. If you look at the values, Ex equal to this is given, it is having a cosinusoidal function of y inside the dielectric, and it decays exponentially outside dielectric. Similarly, for the antisymmetric mode also, only thing is that it has a sinusoidal variation inside dielectric. So, at y equal to 0 we are expecting Ex equal to 0. Let us see the plot. So, it looks very similar to Hx variation of Tm mode. So, for TE0 mode again we do not have any cutoff frequency for TE0 mode. So, in this case the field component Ex is maximum on zx plane, and it decays above and below, and inside air it decays exponentially. Look at the first antisymmetric mode of Ex. On zx plane again Ex is 0, and in air it decays exponentially. So, the cutoff frequencies, some characteristics are described here. TM0 mode and TE0 mode, they have no cutoff frequencies. For other modes, the cutoff frequency can be solved from here, twice d by lambda naught. Lambda naught is the wavelength in free space. This is equal to m by 2 into square root of epsilon r minus 1, where epsilon r it represents the dielectric constant of the slab. Then for symmetric mode, m equal to 0 or any even number, and for antisymmetric mode m equal to odd number. So, from this then we can calculate the cutoff frequencies for TM1, TM2, TM3 as well as TE1, TE2, TE3, all different modes. So, remember TM0 and TE0 mode, they have no cutoff frequencies. So, why we are discussing about the surface wave modes for a dielectric slab? So, we can design actually dielectric channel which are popular as guiding structure at millimeter wave frequencies like image guide, insular image guide, and some other forms like non-radiating dielectric, NRD guide we will see later. So, for that the concept of the surface wave modes is very important. We will be using this concept to see how those dielectric guides they support electromagnetic wave propagation. So, next we consider another scenario. In this case, dielectric slab it is placed on a conductor ground plane. Again the wave propagation in z direction, but the perpendicular direction is x here. Let us go directly to the solution. It can be shown that this dielectric slab backed by a ground plane, it can support TE mode as well as TM modes. So, we will see T for TE and TM, again we have TE0 and TM0 mode, and these two modes does not have any cutoff frequency, and it creates a lot of problem for any printed circuit board lines. For example, if we fabricate a microstrip line or a coplanar waveguide in any printed circuit board technology. So, microstrip we have a strip over a dielectric slab and below we have ground. So, we will be facing a similar problem just like this what we are going to discuss here. Similarly, for the CPW line, the CPW line it sits over a dielectric slab and usually the ground plane it's infinite. So, again it is somewhat similar to this problem. Also, we have conductor backed CPW line. In that case, we use a ground plane, another second ground plane in addition to the top layer CPW line. So, let us see then what problem we face for the surface wave in a grounded back dielectric. So, the first one is TM modes. So, the dominant electric and magnetic field components are Ez, Hx and Hy. If you look at the solution for Ez component it's in which direction? It is in the direction of electromagnetic wave propagation. So, Ez we have a metal here as the ground plane. So, it is parallel to this metal plane, and now from the boundary condition what we have seen? We have seen that there can't be any tangential electric field component on metal. So, without going to the final expression, we can expect or estimate that there should not be any Ez component for at x equal to 0. Now, let us go to the solution. So, inside dielectric x equal to 0 to d. So, you note down that we change the direction of x, it is perpendicular to ground plane. So, inside dielectric we have sinusoidal variation of Ez component. So, at x equal to 0 it is 0, and then it increases, it becomes maximum at the dielectric air interface, and once in air you see it decreases exponentially. So, from d for more, so x for more than d it decreases exponentially. Similarly, the Ex component it is perpendicular to ground plane, right. So, on the ground plane it may have maximum value, and look at the expression, it has cosinusoidal variation. So, at x equal to 0 it is having maximum value, and then it decreases with increasing x, and inside air just above this dielectric it decreases exponentially. For TM0 mode we do not have any cutoff frequency, it can start right from DC. For other modes we have the cutoff frequency Fc, this is equal to Nc divided by twice t square root of epsilon r minus 1. This is the thickness of the dielectric layer. So, it depends on the thickness of dielectric layer as well as epsilon r of the dielectric. And for TM0 mode, you remember it has no cutoff frequency. For other modes, then we can calculate it from here. Now, this TM0 mode, it has detrimental effect for microstrip lines. Why? Let us take first one example. So, if I plot the electric field of a microstrip line, how it looks? Let us say this is the top strip and this is the ground plane. So, I am drawing the cross sectional view of a microstrip line, and now what we considered for the grounded dielectric slab problem, perpendicular direction is x direction and the wave propagation direction, this is z direction. If I look at the electric fields, it will be perpendicular to both strips and the ground. We have also some fringing field components here. So, we see that for microstrip line, dominant component of electric field is Ex component. Now, for a grounded dielectric slab, what we have seen? For a grounded dielectric slab, if I consider again the cross sectional view, so perpendicular direction is x, wave propagation direction is z. So, in this case, the dominant electric field components are Ex and Ez component. So, Ex, this is maximum on the ground plane, and Ez component, this is maximum at the interface. Since we have Ex component for the microstrip line as well, so this microstrip line field component, it can easily excite the surface wave. We have a field coupling from the Ex to Ex, and this microstrip line, it can easily excite the surface wave. So, in fact, it microstrip line always excite this surface wave, which is given as TM0 mode, which has no cutoff frequency, and the power lost to this surface wave, it actually increases. It is a function of thickness with respect to lambda or lambda g. So, the amount of power that is lost to this TM0 mode excitation, it is directly proportional to d by lambda g. So, higher is the thickness of your substrate, higher will be power lost to the surface wave mode. Now, at millimeter wave frequencies, lambda g is very small. Already we have seen that typically at 60 gigahertz, if I calculate lambda g at 60 gigahertz, this is equal to let us consider a typical substrate with epsilon r, let us say this is equal to 4, then lambda g is 5 divided by square root of epsilon r. So, it is coming how much? 5 divided by 2, 2.5 millimeter lambda g. We can neglect the effect of surface wave only if d by lambda g is smaller than 1 by 100. So, what do you expect? Even if I consider a 10 mil or 20 mil thick substrate, we can't neglect the effect of surface wave at millimeter wave frequencies. And the problem of surface wave is that not only the power loss, but also crosstalk between two side by side lines. So, if I have one more microstrip line here, it is carrying, let us say, another signal. So, we will be having coupling through the surface wave. This is not just by the fringing fields. So, at millimeter wave frequencies typically we face this problem, the detrimental effect of TM0 mode, particularly for microstrip line. Now, the next mode is TE mode. In this case, the dominant electric and magnetic field components are UI, HZ and HX. So, what is the direction of UI? UI, it is perpendicular to propagation direction, and the ground plane it is in ZY plane now. So, UI is also parallel to the ground plane. So, on ground we do not expect any UI component since it is a conductor. Now, look at the expression. Inside dielectric we have sinusoidal variation. So, at x equal to 0 UI is 0, and then it increases at as we increase the x, and it has maximum value at the interface, and inside air it decreases exponentially. TE0 mode, it does not have any cutoff frequency. For other modes the expression is little different than TM mode's cutoff frequency. We can calculate Fc as twice n minus 1 into c divided by 40 square root of epsilon r minus 1. So, c is the velocity of light in free space, and d, this is the thickness of dielectric slab, and epsilon r, this is the dielectric constant of this slab. Now, usually for microstrip line we do not face any problem for TE modes, but we face problem for the CPW lines. Why? Let us first see the field plots of a CPW line. So, how the CPW line it looks? Let us say this is the central strip of a CPW line, and we have left and right ground plane. So, I am drawing the cross section, and it is sitting over a dielectric. Now, if I plot the field, so it starts from signal line and terminates on the ground, left and right ground. Now, what is the wave propagation direction we considered? Wave propagation direction is z, and the perpendicular direction we considered x, and this side, this is the y component. And if I go back to the solution, you see in the solution we have EY components. So, EY it is maximum at the interface, and then on ground plane obviously it is small, but since we have EY component for TE0 mode which has no cutoff frequency, then this TE0 mode it is easily excited by the CPW lines, and we have similar problem as we have seen for the microstrip line. So, somehow then we have to avoid this TE0 mode or the effect of TM0 mode. In practice, there is no way to completely avoid the effect of this TE0 or TM0 mode, but still we have some solution by which we can reduce the coupling to some extent. So, for example, if I consider the effect of TM0 mode and how to reduce it. So, let us go back to the diagram. So, for TE0 mode, for TM0 mode, what we see? The main problem is coming due to this x component of electric field, which is perpendicular to ground plane. Sorry. Now, I want to avoid coupling between these two side by side line, and so what we have to do? We have to do some modification which does not couple power to the surface wave mode. So, what we do practically? We will be using one more strip in between these two microstrip line, and then use a metal via which connect this top strip to ground. Now, since the electric field Ex component is parallel to this via, it will be suppressed by this via. So, the only thing what we have to do, we have to use periodic vias to suppress this Ex component. So, in z direction these vias will be periodic, and the separation typically we use less than lambda g by 4 at the highest frequency of operation. It can suppress this coupling to some extent, let us say by 10 to 15 dB, but it can't avoid the effect completely. Okay, so let us take one break, then we will see the other parts.